Hi guys, Buildzoid here, and today we're going to be doing another X670 motherboard PCB breakdown. This time it's the ASUS ROG Crosshair X670E Gene. This board was sent to me by ASUS, so big thank you to them for sending over the motherboard, and at the time of recording this video, the board tends to go for around $600. And with that out of the way, let's get into it, because there's a lot to talk about with this board. First, let's go over the rear I/O, where we find a clear CMOS button, a BIOS flashback button, so you can actually update the BIOS of this motherboard without even having a CPU installed. There's a PS2 port, because this board is meant for extreme overclocking, and in a lot of extreme overclocking scenarios, you can end up with your USB ports not working anymore, whereas the PS2 port pretty much always works, so that's why that's there. Speaking of USB ports, there's 7 USB Type-A ports, and there's also 3 USB Type-C ports over here. If you want more details on the support, like functionality those support, I recommend you check out the motherboard manual. There's Intel 2.5 gig LAN, and we've also got Wi-Fi 6E, as well as a full set of audio ports, including an optical output. So, yeah, basically fully featured rear I/O. For a high-end motherboard. Like, yeah, I don't think they're, well, I guess you could argue that 10 gig LAN is a thing on a lot of high-end motherboards these days, and, well, this doesn't have that, but other than that, this does kind of have everything. So now let's move on to the internal functionality that I personally find a lot more interesting, which is things like the postcode. Very helpful if you're doing overclocking, as you just get information about why the system doesn't want to post any longer, though on AMD motherboards it isn't generally as helpful as it tends to be on Intel boards. Below that, we've got color-coded troubleshooting LEDs, which are basically redundant because the postcode does the same thing and gives you more details than the LEDs do, but I guess if you just want to know what's wrong at a glance, the colorful glow might be a bit faster than, figuring out what postcode you're looking at. Power button, flex key, so this by default acts as a reset button, but it can also be rebound to a bunch of other functions like safe boot, or I think go straight to the BIOS. Below that we have a retry button. This is basically a hard reset. So basically, in certain overclocking scenarios, you can lock up the CPU and the motherboard so hard that, like, the reset button stops working. I think I've even managed to get some AMD motherboards to the point that, like, holding the power button for 10 seconds also stops working. Well, this button right here doesn't care about how locked up your CPU is or chipset is or anything else on the board, like how crashed the motherboard is. Because what this button does is the equivalent of power cycling the power supply. It just cuts power. It will always reset the system. And so it's really helpful in it's helpful if you lock up the motherboard really, really hard, because you don't have to go all the way to like turning off the power supply and then turning the power supply back on again. And it can also be helpful for forcing the motherboard to retrain memory settings, though in my experience, that's like AMD's memory controller doesn't really seem to struggle with. Well, AMD's memory controllers generally seem to either boot or not boot. They're not like the Intel memory controller where sometimes just power cycling it a bunch of times will eventually get certain settings to work. It's more of an Intel thing than an AMD thing, but that is another use for this button. Below that, we have a dedicated hardware like safe boot button, and I am very sad to say that the safe boot button does not work. Which is, as far as I know, that's just a problem with AMD motherboards, because the AMD AGSA has a built-in like overclocking recovery function that barely ever works, but because that that unreliable automatic overclock recovery system is in the AGSA, motherboard vendors like ASUS are just not able to implement a safe boot button that works properly, which is probably why like MSI just doesn't bother with having safe boot buttons on their AMD boards. Because yeah, both Gigabyte and ASUS have tried to get like a working safe boot onto AMD motherboards at this point. I've never seen it actually work. So yeah, that's really unfortunate, because this button on an Intel motherboard is amazing. It's so convenient. Yeah, unfortunately, it just does not work on AMD motherboards, so that kind of sucks. Down here, we have the PCIe slot release button, right, for this over here. There's also, I guess I should mention this, there's a riser card for your M.2 drives called the Gen Z.2. I don't really do M.2 drives, so I don't really care. But one of the M.2 one of the M.2 drives that goes onto this is PCIe Gen 5. There's an internal USB Type-C header. The board does unfortunately only has 4 SATA ports, but it is an MATX motherboard, and there's kind of a lack of space. Like I think it would be nice if there were more SATA ports, but unfortunately there's really not any space left for that kind of thing on this board. Anyway, then down here we get more fun overclocking things, including a bunch of voltage read points along the bottom edge right here. And I'm a really big fan of how ASUS does their voltage read points, because on a lot of motherboards you'll just get like solder bumps, and then if your multimeter probes aren't very sharp, then they have a tendency to slide off of the solder bumps, and it's just kind of annoying. These are plated through holes, so your multimeter probes just kind of sit in them, regardless of how dull they are. So yeah, I do appreciate these not being solder bumps, and you can measure basically every voltage you could want to check during like overclocking with these, so that's pretty cool. We've got BCLK up-down buttons. These are very handy if you're doing like frequency validation, so like max CPU frequency, max memory frequency, that kind of thing. It's just more convenient to have physical buttons on the board than having to like mess around with some software inside Windows. Oh, I guess you could technically use a keyboard shortcut for raising BCLK up and down, but I prefer buttons on the motherboard. Then over here, we've got a slow mode switch. This just lets you set the CPU to the lowest possible like CPU speed. Again, this is primarily for LN2 overclocking, because you don't necessarily want to be saving screenshots at 6 gigahertz, or setting up your benchmark at 6 gigahertz. That's just kind of unnecessary. So slow mode is there so that you can basically mess around in the operating system while on LN2 without the CPU going at full speed. Below that, we have a reserved switch, which historically on ASUS motherboards would just preload some extra voltage settings for LN2, preload some extra BIOS settings for LN2 overclocking. It's not necessarily just voltage settings, but that's usually most of what it does, is adjust some of the voltages to deal with some of the issues that you run into with running CPUs at very low temperatures. Over here, we have an LN2 mode jumper. This removes a bunch of like voltage safety restrictions, as well as also preloads some extra voltages for, again, LN2 overclocking. So yeah, we've got all of the sort of extreme overclocking stuff over here. There's an oscilloscope. There's a header for hooking up the ROG True Voltition, which is like a mini oscilloscope that the motherboard comes with. I'm not tested how well that works just yet. Yeah, that's what that header is for. And is there anything that I'm forgetting about down here? No. Well, not specifically in this area, so let's move on. Over here, we have a PCIe PCIe speed switch. So if you're using crappy riser cables that don't do PCIe Gen 5 or don't do PCIe Gen 4, you can use this to manually lower the PCIe speed of the motherboard from PCIe 5 to like 4 or 3. Without having to go into the BIOS. Because normally if you had like let's say a PCIe Gen 3 riser and you have a Gen 4 graphics card and you hook this up to the motherboard, you won't be able to boot basically, because the GPU will not be able to run the GPU will try to run at Gen 4, but if your riser can't do Gen 4, then the GPU can't talk to the motherboard and you get no display out. So in that scenario, normally you'd have to go into the BIOS, then configure your PCIe link speed down to Gen 3, and then your GPU would start working. With this, you don't have to do that. You can just use this switch to permanently set the motherboard to Gen 3, and you don't have to deal with the whole going into the BIOS to configure the PCIe speed. So that's pretty cool. Then you get your PCIe 1X, 16X Gen 5 over here, which this primarily is for lowering the speed of the X16 Gen 5 slot there. There's an M.2 slot over here. And then we've got these white fan headers scattered around the board, and I really like these, because these are full-speed fan headers, and basically what that means is by default they run at 100% fan speed, which is very convenient if you're like me and you primarily use test benches where you don't care about how much noise they make, right? Because a lot of the time if I'm just setting up a test bench for some benchmarking, like, I just want the fans to go as fast as possible. right? So I do appreciate the fact that like ASUS has these on a lot of their extreme, like more extreme overclocking oriented boards, like the Apex boards tend to have these as well. So yeah, I think those are cool. And if I remember correctly, you can manually tune the fan speed on them in the BIOS. So it's not like they're permanently locked at 100%. They just default to 100%. And I think that covers all of the sort of features, internal features on this motherboard. So yeah, this thing is packed. It's an MATX board, and there's really no empty space on the PCB. So it's not really surprising. Anyway, let's talk about the power delivery. So in typical high-end X670 motherboard fashion, we've got, actually, I don't think there's even low-end X670 boards that don't have the obligatory and unnecessary dual 8-pin power connectors, because, well, a single one of these 8 pins can easily do over 300 watts of power. There's no CPU that you can put into this socket that'll pull 300 watts of power, so this 8-pin over here is entirely optional. Basically, if your power supply, like, here's the thing, if your power supply has dual 8-pin power connectors, you can plug them in, you can plug both of them in, and that's just fine. But if your power supply only has a single 8-pin, you don't have to worry about this secondary 8-pin on the motherboard. It really doesn't do anything, especially since ASUS is using the actual high current version of the 8-pin power connectors. So these have solid metal pins, so they can handle even more current than like your basic 8-pin power connector, which already does over 300 watts. Like, I'd like to point out that old AM3 Plus boards that support the FX9590, a 220 watt TDP CPU, use like folded metal 8 pins and often only have one of them. So the like dual 8 pins that we see on a lot of modern motherboards are extremely unnecessary. So yeah. Anyway, but you know, it like the extra 8 pin doesn't hurt anything by any being there, but you don't, if your power supply doesn't support dual 8 pins, it doesn't matter, is basically what I'm trying to get across. So anyway, now let's talk about the actual VRM. And so that's all of this, and it's got a rather unique layout. I mean, at a glance, it looks pretty standard, but actually once you get into it, it's pretty unique because, yeah. So what's going on here is, down here we have the vMISC, so the V miscellaneous rail. Then above that, we have one phase of vCore. Then above that, we have the VSOC rail. And then the rest of this is more vCore, which I guess I should put over here. So yeah, that's the rest of the vCore VRM. And it's a bit weird because the CCDs are over here. So your power delivery for the CCDs is like primarily really far away from them, relatively speaking. I guess it doesn't really make that much of a difference. If you rotated the CPU, the CCDs would move like a centimeter maybe. Now I guess if you move the VRM, might get significant, not really. But yeah, so it's a bit weird that ASUS decided to put all of the vCore VRM up here. But I suspect the reason they decided to lay the board out this way is, so like putting the SoC VRM in between the vCore phases basically reduces the thermal density of the vCore VRM in this area. On most motherboards, it's pretty typical to have a VRM hotspot like right here, because this would all be vCore, and then like your SoC VRM would be hanging out over here. Because ASUS puts the SoC VRM over here, and most of the vCore VRM lives up on the top edge, the actual hotspot for this VRM is right here, instead of here. And I guess the logic behind doing that on this board is that these capacitors over here, these are SMD polymers, and while these do have better like ESL than your through-hole polymers, these generally do not have as high a like thermal endurance rating as your through-hole capacitors up here do. So I'm guessing that's the reason that ASUS is still doing this, because the thing is on like X470 motherboard, like ASUS I think first did this on an X470 motherboard. But there, most of the vCore VRM was actually in this area. and so it pretty significantly affected like the hotspot effect of that VRM. Whereas here, it really looks to me more like ASUS decided to move the hotspot away from this area of the board. It could also be, I guess, for some things like the USB 4.0. I think that's the USB 4 chip over here. So, yeah, an interesting layout. And the main reason they're doing this is just for thermal performance. Like it basically just shifts around the heat distribution of the vCore VRM is what it does. So yeah, interesting though. Like you don't really see many other. Actually, I don't think anybody else does this. This I'm pretty sure is unique to ASUS. Anyway, in terms of controllers, the vMISC rail is controlled by this chip over here, which that is a Renesas RAA 2296, 9613, and that's a two-phase controller. So we've got a two-phase V miscellaneous rail. Then the SoC and the vCore VRM are controlled by a chip on the back of the board. And this is unfortunately some kind of rebranded. I suspect it's a Renesas part, but yeah, ASUS has their main VRM controllers just rebranded because it's part of their like Digi Plus marketing thing. So I only know this part as an ASP2205, and I have no idea what it actually is. I would assume it's some Renesas RAA 22 series chip. That might be where this 22 comes from in the full part number, like in the ASUS part number. Anyway, this is an 8+ 2-phase. Actually, I don't know if it's an 8+ 2-phase chip, but here it is running in an 8+ 2-phase configuration. So we've got 8 phases of vCore and then 2 phases of SoC VRM. Right, so the SoC is like 1, 2, and the vCore you have like 1, 2, 3, 4, 5, 6, 7, 8. So pretty standard for a lot of motherboards these days to basically just put their power stages and inductors in parallel. So you have one PWM signal going into 2 power stages at the same time, so they switch on and off at the same time, and they're in phase with each other. But the reason this is done, especially like once you hit a very high phase count, like there are benefits to just having more phases, but they're very much diminishing returns past a certain point. And 8 phases is well into the diminishing returns for increasing the phase count further. So I really don't have any complaints about ASUS doing this over here. Like this is completely fine. And also, actually, I think a lot of the other motherboards in this price range are also just putting power stages in parallel because, yeah, when I say there's, like, going past 8 phases, the diminishing returns are very diminished. So, yeah. Anyway, so that's the control scheme of the VRM. Now let's talk about the actual power stages. And for the power stages, ASUS decided to go with Vishay's SIC 850 series, 850s. These are up to 110 amp smart power stages. And unfortunately, I don't have any documentation for these. So we can't do the usual like theoretical VRM heat output calculations that I normally do for PCB breakdowns, and instead I had to go and actually test the thermals of this VRM. So in order to sort of try isolate the thermal performance of the power stages from the heatsink design, I ran the board without a VRM heatsink. In Prime 90, I ran the board without the VRM heatsink, Prime 95 on the 7950X with, Prime 95, 128K FFT size, 7950X at 4.8 gigahertz, 1.1 volts, which led to the motherboard reporting a current draw of about 200 amps. I've upgraded the cooling system on the 7950X, so that's part of that. For comparison, Cinebench at 5.45 gigahertz pulls 180 amps. So if Prime 95 at 1.1 volts doesn't sound that heavy, it actually pulls more current than Cinebench does. So yeah, that's why I'm testing the way I am. It doesn't sound like the CPU is working very hard, but I assure you it is pulling a lot of current and running very hot. So anyway, in that test scenario, and this was run, like I ran this for over an hour in a 22 degrees Celsius ambient room. This part of the VRM ended up at 93 degrees Celsius, which is a perfectly acceptable operating temperature for power stages to be at. This part of the VRM was closer to 80 degrees Celsius, so yeah, putting the SoC VRM sort of in between the vCore phases significantly reduced the operating temperature of this area of the board. Like, as you go away from the hotspot, the VRM temperature actually drops off very quickly. Like, this power stage is closer to 80 degrees than it is to 90 degrees Celsius. I unfortunately don't have a thermal camera, so it's really hard for me to have, like, exact temperatures for, different parts of the board. I had a K-type thermocouple stuck to the hotspot of the VRM itself, so I'm rather confident about this temperature, but for the rest of the VRM, it's kind of like, yeah, approaching 80 degrees as you get away from the hotspot. And so, yeah, the VRM absolutely can power any CPU that you can put into the socket without the VRM heatsink, which is pretty standard for high-end actually for all X670 motherboards, I'd say. So yeah, no, like, in terms of power delivery capabilities, we have the standard, like, it's the standard X670 motherboard affair of massive overkill. No surprises here. And nothing to complain about. Well, there is one thing to complain about, and it's not related to the power handling capability of this VRM. It's the fact that there's no VRM temperature sensor exposed in hardware info. This is, as far as I know, pretty standard for ASUS motherboards, but really annoying. Most other manufacturers will have a, NTC thermistor somewhere in the VRM that's connected to the Super I/O so that you get a VRM temperature reading. Now, sometimes they don't put that temperature sensor in the ideal location, but you always get something to indicate what temperature the VRM is at. ASUS, on the other hand, doesn't give you any kind of temperature sensor like that. Now, the VRM still has temperature sensing because these wouldn't be smart power stages if they didn't have integrated temperature sensors, and you can't really have a properly functional load line if the VRM isn't able to compensate for thermal effects. But the thing is, so basically the ASP2205 is monitoring the VRM temperature through the actual smart power stages, but when it comes to being able to get a VRM temperature reading from the motherboard in hardware info or some kind of software, yeah, that's not a thing with this board, which is quite frustrating. It's not a big deal. Like, this VRM really shouldn't overheat under any scenarios, especially since it does come with a VRM heatsink, right? Like, keep in mind, I tested it with no VRM heatsink and it still stayed under 90, and it's still only maxed out at 93 degrees Celsius. Also with no airflow, no airflow, no heatsink, truly a VRM torture test. So, yeah, it's just kind of annoying that, everybody else has temperature sensors. They don't always label them properly. They don't always put them in the correct location, but you always get some indication of what temperature the VRM is at. You don't get that with this board. And I am kind of disappointed by that. It's not a real, it's not a problem. It's just kind of annoying that there's no temperature sensor. Oh yeah, in terms of actually powering any CPU that you can put into the socket, this VRM is way more than enough. In fact, this VRM would maybe be a bit more efficient if there was fewer or lower rated power stages, because a lot of the really high current rating smart power stages out there don't hit the peak of their efficiency curve until 20 amps or even 30 until 20 amps output current. And the thing is, with 16 power stages at 200 amps, you're only each power stage is only handling about 12 amps of current, right? 12 to 13 amps of current. So arguably this is too much in terms of the power stages that ASUS decided to use. However, without actually testing it, it's hard to say for sure, but yeah, I do kind of wonder if this might not be if it might not even be possible to get better temperatures with maybe slightly lower current rating power stages. Because yeah, a lot of the really, really high current parts, they don't hit peak efficiency until you're at 20 amps output or higher. So, and 20 amps output on, this VRM would mean 320 amps, which there is no CPU that you can put into the socket that'll pull that much current. So, Yeah. But anyway, like it can still run it, like you can still run it without a VRM heatsink and it won't overheat, so that's really not a, like it's not a practical complaint. It's just kind of like, I do wonder if, you know, this might not be like so far past the point of unnecessary that it's almost detrimental, like it's maybe even detrimental to the VRM efficiency. But anyway, let's talk about the other power rails. The SoC VRM is more of the same power stages, except now each of them has its own PWM signal instead of two of them sharing a PWM. They're not really sharing the PWM signal, they're just following the same signal. So here, each of these gets its own PWM signal from the ASP2205, and the SoC rail doesn't really ever have to handle more than like 20 amps of current, so this is mega overkill. Unless we see some CPU with some kind of giant iGPU, which I don't think is very realistic. And then the vMISC rail just uses a bunch of ISL 99390s, which are actually sort of the part that I was thinking of, where I was like, you know, I wonder if ASUS had used the ISL 99390s, because these are 90 amp smart power stages. And these also don't hit the peak of their efficiency curve until like 20 amps output, but these are rated even higher, so they should peak even later in terms of output current. So I do kind of wonder if like it might not have been better to just use a bunch of ISL 99390s in the VRM, but it doesn't really, like the VRM being at 93 degrees or 90 degrees really doesn't make a difference. So yeah, it's not really, or more like the hottest part of the VRM, because the rest of the VRM is actually cool. It's just like this spot right here, which, you know, that ends up running kind of hot. So yeah, anyway, the vMISC rail has to output even less current than the SoC rail, so this is massive overkill. In fact, there's some high-end X670 motherboards that have a single-phase vMISC and vSoC. And then there's also like Gigabyte and ASUS where they just slap a two-phase VRM on both of them, and it's like, yep, like it's just kind of there. Massive overkill. So yeah, in terms of current handling capability, really nothing to complain about. So anyway, let's talk about the power filtering. And I will go ahead and say that I have actually taken oscilloscope measurements of this board as well as a lot of the other X670E motherboards. And the data, like so the test results for that are already available to the patrons, but I will be making a video about that in the future. But I've already measured the voltage regulation performance of this board. It is very good. In fact, it's the best motherboard I've measured so far. So yeah, and that's actually really surprising considering the like minimalist approach that ASUS has taken to the output filtering. Well, the inductors are pretty standard. These are 330 nanohenry inductors, which is a little, honestly, actually kind of on the high side for a modern VRM in terms of inductance per, like in terms of inductor inductance. But at the same time, when you're putting your power stages in parallel and your inductors in parallel, that inductance effectively gets cut in half because both inductors get connected to the 12-volt power plane at the same time. So, like this is pretty standard for a VRM where you have the power stages and inductors running in parallel. Where was I going with this? Yeah, so nothing really that surprising there, but the capacitor configuration is just insane because the VCore VRM's bulk capacitance is this capacitor, these two capacitors, and these two capacitors. The total bulk capacitance on this VRM is made up of three 560 microfarad, that's not 560, 560 microfarad, 6.3 volt, Nichicon, I might actually, yeah, you know what, we'll just write out the whole thing. Nichicon FP10K capacitors, and so these are rated for 10,000 hours at 105 degrees Celsius, and they're, you know, through-hole polymers. And then these two capacitors over here, these are 150 microfarad. I don't know what the voltage rating is on them. It really doesn't matter. They're on the V-core rail. Like, the reason you see like 6.3 volt capacitors typically used on the output filter of V-core VRMs on motherboards is because those 6.3 volt capacitors are also used for filtering the 5 volt power rail going around the board. They're used for filtering like your USB ports, and they're just kind of used everywhere. So it's like, well, we already have like this, and you don't really get like a big benefit using like 2.5 volt capacitors instead of 6.3 volt capacitors. So you just see 6.3 volt capacitors kind of used everywhere there of it, like anywhere except the 12 volt rail on a motherboard is kind of the standard application of 6.3 volt capacitors, because the 12 volt rail, you know, is 12 volts. You can't use 6.3 volt caps on that. But yeah, the total bulk capacitance on the V-core VRM of this motherboard is like nothing. But the voltage regulation is actually really, really good. It like, you'd think with this little bulk capacitance, like there'd be a significant amount of overshoot. There isn't. It's just like the overshoot is in line with other X670 motherboards I've measured, and the undershoot is actually way better. So, yeah, like I am very impressed by what ASUS has managed to do here in terms of voltage regulation, but it's not being done with the bulk capacitors. The socket itself is absolutely packed with multi-layer ceramics, so that's part of it. But the other thing is, like, and this is pretty standard for a lot of high-end ASUS motherboards, is ASUS just has these, like, small groups of multi-layer ceramics hanging around the CPU socket, acting as just more V-core power filtering. So like this is just more V-core filtering. And then there's a bunch of multi-layer ceramics that you can't see because there's the holding bracket, like a hold down bracket over them, hanging out over here that are also more V-core filtering. So yeah, there's very little like bulk capacitance, but in terms of multi-layer ceramics, I think this board just has more of them than potentially all other X670 boards. So a really interesting approach to the output filtering on this VRM, because yeah, like I didn't, like I wouldn't think it's possible to have like what is it, like 5 bulk capacitors in total, and 2 of those are like 150 microfarads each. It's like nothing. So yeah, a very, very interesting approach to the V-core filtering, and it works really well. Like I have measured it. It works really, really, really well. Now, the SoC VRM actually makes the V-core VRM filtering look kind of like even more bizarre, because the SoC VRM has these 3 560 microfarad bulk capacitors and this 470 microfarad SMD polymer, and this is a 3-terminal SMD polymer, so that's like the ultra-low ESL version of a SMD polymer capacitor, so that's kind of cool to see. The VMISC rail has a single 560 microfarad through-hole capacitor, then a bunch of multi-layer ceramics hanging right off of it, and then there's also this 3-terminal 470 microfarad cap back here. So yeah, like the SoC VRM actually has like more bulk capacitance than V-core does, which is just so strange to see. Because typically, like there's a lot of motherboards where you get like one capacitor per, like one bulk capacitor per phase. This board doesn't even do that, right? So yeah, a very, very interesting approach to the VRM design from ASUS, but it works, so I'm not going to complain about it. And for input filtering, this is sort of like, there's a lot of input filtering, but that's standard for ASUS motherboards. So you've got all of these 56 microfarad SMD polymers over here. I don't really, like for input filtering, I don't really think there's much benefit to using 500 like SMD polymers instead of through-hole polymers, because the thing with input filtering is the frequencies that the like the bulk capacitors are filtering are much lower. So I really think that the reason that they're using these 560s over in this area is just space constraints rather than like performance optimizations. But yeah, so you've got these 560s on the front, and I mean 56s on the front, more 56s on the back. There's 11 of them in total. And then on the top edge of the board, which is where sort of the hotspot of the VRM is, you have these through-hole polymers, and those are 270 microfarads. And those are, of course, FP10K capacitors, so rated for 10,000 hours at 105 degrees. And that's also why I kind of suspect that, like, maybe the whole moving the hotspot over here was just like, well, these are SMD polymers, and they generally don't come in really high endurance ratings like your through-hole capacitors do. So that would kind of explain to me why they wanted to move the hotspot away from that area. It could also be for the other, controllers in that area of the board. Yeah, so a very substantial input filter, and then like minimalist output filtering. In terms of bulk capacitance, in terms of ceramics, there's actually a lot more ceramic capacitors on this board's V-core than I'm used to seeing on most other motherboards. So yeah, I really like the. It can power any CPU you can put into the socket. The voltage regulation is excellent. There might be other motherboards that are on par with this, but I don't think there's any, like, I think it's pretty unlikely that there's any motherboards that are better than this. Yeah, so I'm just overall very impressed with the V-core, like the CPU power delivery. And now let's talk about the VDDIO memory VRM, which is massive overkill. This is the biggest VDDI, like this is probably the biggest VDDIO mem that I've on any motherboard. It's huge. It's 2 phases, controlled by this chip down over here, and I should have labeled it. So VDDIO memory, and this literally just powers the memory controller. Like, it's monstrous for what it's doing. And yeah, it's a 2-phase. It's controlled by a Infineon XDPE 192C3B. Wait, C3B 2-phase controller, and we've got these smart power stages over here, and these are TDA 2157s. These are 70 amp smart power stages. Like, there are motherboards out there that have their VDDIO memory rail made up of discrete MOSFETs, like, these guys. And then there's this board where we have TDA 21570s for VDDIO mem, which is like it's just insane. Like, I have no idea why they decided to go with just such a powerful VDDIO memory VRM. Like, it makes no sense to me. But it doesn't hurt it. Well, the only thing this hurts is the overall cost of the motherboard. It doesn't hurt anything in terms of performance. I'm just really surprised by that. So yeah, the memory power delivery is probably the most overkill memory power delivery of any X670 motherboard there is. And the filtering for the memory power delivery is kind of hard to see. I think this is output filtering, but that's a 16-volt capacitor. This is probably more memory VDDIO mem filtering. On the back of the board, this one's easy. This is definitely VDDIO mem. This might be. Yeah, you've also got some ceramics over here for that. So yeah, and this board has a very interesting also like memory topology, because to me at least it looks like ASUS might be using the memory, like the VDDIO mem power plane, as a reference plane for the data queue of at least one, if not both memory channels. Because basically there is a power plane that just goes like this. And that's all VDDIO mem. Like, that just goes from the memory VRM all the way to the CPU socket. And you can't really see it, but there's a, like, what looks to be VD... I didn't want to scratch through the solder mask because, yeah, I don't really want to damage the board. But there's a great big polygon over here that has a trace heading over to the CPU socket. If this was just a big ground fill, I don't think that would make a lot of sense. Also, it's not very visible on this photo, unfortunately. But to me, it really looks like ASUS is using the VDDIO mem power plane as a reference plane for the memory data queue, which is very interesting. I've not seen that on any other motherboard. As far as I know, everybody else is just using the ground plane as a reference plane. That, like, yeah, so, I don't know if that's good. I don't know if that's bad. This is one of those things that you actually have to test. Also, it can, how good the memory overclocking of a motherboard can change drastically with BIOS updates. So, but it is a very unique approach to the memory topology. And speaking of a unique approach to the memory topology, this right here, right, or actually this right here is just a ground polygon that's just, yeah, hanging out over here. I don't know why it doesn't connect to this. I don't actually know what this over here is. I guess it might be VDDIO mem. It might be vCore. I have no idea. I don't get sent full schematics, but yeah, ASUS is doing some interesting things in the memory area of this board. And then, of course, it is a 1 DIMM per channel memory topology. So well, right now, the 1 DIMM per channel memory topology doesn't seem to really have any inherent benefits because so far the Ryzen memory controller seems very reluctant to go over 6400 megabits per second. But maybe with some BIOS updates, we might see 1 DIMM per channel memory topologies having a pretty significant, in theory, a 1 DIMM per channel memory topology should have a max frequency advantage, and a pretty substantial one over any daisy chain topology. Right now we're not seeing that because the CPUs just don't do high memory speeds. So arguably a bit wasted, but maybe this maybe in a 2x32 configuration, this might be better than like a 4x16. Then again, you could always just stick a 2x32 on your daisy chain, and that might actually be on par with this. I unfortunately don't have 32 gig DDR5 DIMMs, so I've not been able to test that. And with the 16 gig DIMMs that I do have, I've not noticed any immediate benefits to this over the daisy chain boards. So yeah, and I think that really is just down to the Ryzen memory controller currently just not doing super high memory speeds. So yeah. It almost feels like this really interesting memory topology might be kind of wasted on Ryzen because the CPU is kind of brick wall at 6400 megabits per second. Well, actually, 6500 megabits per second is doable. It's just also doable on all motherboards in my experience, and not as in 100% stable. But if you just want to run benchmarks, 6500 megabits per second is doable. So yeah, I wish there was a way to see if this actually has any benefits over the other boards, but so far it doesn't seem to, which is a bit unfortunate. Maybe in the future we'll see CPUs that can actually take advantage of this memory topology, but right now, or maybe just BIOS updates that'll take advantage of this memory topology, but right now it doesn't seem to really do anything, which is, well, I mean, it's not yeah, which is just kind of I wish this had benefits right now because, yeah, there kind of aren't any. So, and then I think covers everything there is to say about this board. Oh, I just realized I don't think this has dual BIOS, which is kind of unfortunate. Yeah, there's one BIOS chip right over here, and there isn't another one on the back, and there isn't another one on the front. So, yeah, that's a bit sad. But anyway, that's the Crosshair X670E gene. Probably, I would dare say that this is the best overclocking MATX motherboard for X670. I don't think that there's really any competition in that segment. But, well, I think. I don't think you can get an MATX board with a postcode. So this sort of wins by default, just by having the postcode, and then I don't think you're going to find anything with a better VRM in terms of voltage regulation, so, yeah. Anyway, so that's the X670E, gene. It feels kind of wasted on Ryzen 7000, unfortunately. If the memory controller was better, then I feel like this memory topology could really, could show some advantages over all the daisy chain boards. But yeah, so far that just isn't a thing. Anyway, so thank you to ASUS for providing the motherboard. Thank you for watching. Like, share, subscribe, leave any questions, comments, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp with like a bunch of industrial noise, if that's what you're into. Links down in the description below. So that's it for the video. Thanks for watching, and goodbye.